This is Unit 6, Lesson 2 about graphing exponentials. So the objective here is we're going to do two things. We're going to graph exponential functions and compute compound interest. So graphing exponential functions is actually a large part of the test. There's like 5 questions of a test from it, but it's actually also really easy to do. So we're just going to fly right through that and get to the compound interest stuff, which is much more interesting and much more fun. So to graph exponential functions, you can use the same trick you use for everything. And that is you're going to go ahead and plug in x and see what you get for y, and then plot those points. So the first thing I'm going to do, I'm going to go from -3. I'm going to write 2 to the -3rd. If you put 2 to the -3rd in a calculator, that's the same as 1 divided by 2 to the 3rd, which is 1/8, or 0.125. 2 to the -2nd is 1 over 2 to the 2nd, or 1/4, which is the same as 0.25. Oh, and I'm also plotting them over there on the left as well as we go along. 2 to the -1st is 1 over 2. That's 0.5, so I plot -1.5. And then we have 2 to the 0, which is 1. So we got 0, 1. 2 to the 1st is 2, obviously. 2 to the 2nd is 4. And 2 to the 3rd is 8. When we connect those together, we get that shape for our exponential. Okay, we're going to go the other way too. We can graph decay. So we have 1/2 to the x power. So we're going to do 1/2 to the -3rd. We can put that in the calculator. It's going to give us 8. 1/2 to the -2nd gives us 4. 1/2 to the -1st gives us 2. 1/2 to the 0. 1/2 to the 0 is always 1. 1/2 to the 1 is 1/2. 1/2 squared is 1 over 4. And 1/2 to the 3rd is 1 over 8. So you see it's the same shape graph, but it goes the other way. You'll notice that both of these graphs go through 0, 1. Because anything to the 0 power is 1. All these kind of functions are going to go through 0, 1. The only way it doesn't go through 0, 1 is if you have an a. So if it was like 2 times 1/2 to the x, it would go through 2. If it was 3 times 1/2 to the x, it would go through 3, and so forth and so on. And that's all you're going to do for graphs. You're just going to put them in the calculator and copy what you got. One thing you can notice in both of those graphs is that they keep getting smaller and smaller. One side's going to go way up, and that's going to go up without bounds. It's going to keep going up to infinity. But the other side, you see it keeps getting lower and lower, but it never is negative. And that's not just an issue with the window we chose. That if you could choose the biggest window you ever wanted to choose, and that graph is never going to go negative, right? Because if you do 1/2 to the bigger power, the bottom of the fraction keeps getting smaller and smaller and smaller. But there's no positive power that you're going to do for 1/2 that's going to make that fraction negative. In fact, there's no negative power either, because that's just going to be a reciprocal. It's not going to change the sign of what's going on. So that line then, y equals 0, that this graph gets closer and closer to but never crosses or even equals, has a special name. It's called an asymptote. That's how you pronounce it. It's asymptote. The P is silent and the AS sounds like ass, so asymptote. And so that's what that is. When they talk about an asymptote, we're talking about a line that the function gets closer to but never actually crosses. So let's talk about interest. Now a few things I want to define before we get into how to do the calculations. When we do interest, P is going to be the principal, which is the initial initial amount borrowed for the loan. T is going to be the time of a loan, and that's going to be measured in years all the time. And R is the rate, which is the annual interest rate. So that's the annual, of course, means yearly. That's the yearly interest rate. So if you've done interest before, you probably did this equation. And we're going to use an example. We're going to use a mortgage example. So this is going to be a $200,000 loan at 4% interest, and it's going to be over 30 years. So let's go ahead and calculate this out. So if you've done interest before, you've seen simple interest, where you take the principal times the rate times the time, and that gives you the amount of interest of the loan. So if we did this with our example right here, we do 200,000 times 0.04. Don't forget to change percent into a decimal, and then times 30 years. And at the end of the day, if you took a $200,000 loan at 4% interest for 30 years, using simple interest, you would owe $240,000. Not too bad for me, pretty good for me if I'm the bank, but wait. If you really think about what's going on in that loan, that's not really fair. Because at the end of 30 years, when you've accrued 30 years worth of interest that you haven't paid me yet, you're still only paying interest on that original principal, that $200,000. On year 30, you're not paying you're getting interest-free money, because the interest that you already owe me has not been paid back, and you're not paying interest on it. So what I would rather do as a loaner is I would rather you pay interest on the money that you haven't paid me back yet. So I need you to pay interest on the interest, really. And that's called compound interest. And let's see what's going to happen there. forget that, right? Forget that original thing. I want to pay interest on the interest. So instead of just calculating the interest at the end of a loan, I'm going to recalculate the interest at every year of the loan. And then that's going to make the amount of money you owe me grow by the interest rate. So we're going to use that growth formula just like you use for population. So it was y equals a times b to the x. And in this case, y is the amount owed, a is the principal because that's the initial amount of a loan, and then b is 1 plus the rate. Remember that was always b is the growth factor. That's the growth factor. And then that's going to be raised to a t power because I'm measuring in time. So x is the t. For the instance of this loan, that's 200,000 times 1 plus 4% to the 30th power. And when we calculate that out, it's that number, $648,679.50. Whoa, hey now. See, that's a lot better than what I had before as a loaner. And it's not just ripping the people off. I mean, that's a lot more fair because it's not fair to the bank to be able to get interest-free money to get, be using the accrue interest and not have to pay it back. So, but I say, if I as a bank can let the loan, compound every year, and that's good, then clearly compounding it every month would be even better. So now we do that, but when we compound it every month, we have to do a couple of adjustments. Because R is a yearly rate, the monthly rate is we have to divide that rate by 12. So R divided by 12. And since time is measured in years, we have to adjust that to account for the number of months. So we're going to do that. The time is going to be 12t because there's 12 months in a year. So you multiply that number of years times 12, and that gives you a number of months. Okay, so this is what our new formula looks like. A equals P times 1 plus R over 12 to the 12t. And I plug in my R, T, and P. All right, I put that in the calculator. I calculate it out. And this time I have 662,000. Better, getting better. But we're still not where I want to be as a bank. I want to maximize my profits, of course. So we can make a more general equation that fits with that, right? Where instead of 12, I replaced it with n, because 12 was really, if you think about it, the number of times we did this compounding every year. So when we replace this with n, we have a general formula that can do different compoundings for different times. So if I wanted to do weeks, I would put in 12 for n. If I wanted to do months, I would put in 12 for n. If I wanted to do weeks, I put in 52. If I wanted to do days, I put in 365. But clearly, the more times I compound, the more money I'm going to get. So what I would like to know is what happens when the number of times I compound is infinity. What happens if I'm compounding not every second, not every day, not every week, but every moment of every second, okay, all the time. There's an infinite number of times that I compound each year, because that's going to make me the most money. What's the limit of the amount of money I can make here? That's what I want to know. Okay? Well, in order to solve this, I'm going to set something up. So I'm going to describe this letter U, and U is going to equal N over R. And I can't explain why I'm doing that. It's just going to work. So if U is N over R, then if I do 1 over U, the reciprocal of that, that means 1 over U is going to be R over N. And if I cross multiply U equals N over R, I'm going to get U times R equals N. So those three things have to be true as long as I assume that U equals N over R, which I have to because I set it up that way. So now I can replace some of the things in my formula, okay? And the other thing I know is since U times R equals N, and R is a fixed amount, right? R is our rate, then if N goes up, so does R, and if U goes up, if N goes up, so does U, and if U goes up, so does N. So if U goes to infinity, N goes to infinity as well. So I just replaced that. Remember I said R over N is 1 over U, as written in blue, and I replaced the N with U times R, and that's going to help me out here. So, okay, so I'm not worried about R and T in this situation because those are fixed. I can't change the rate of a loan. I can't change the time of a loan. All I'm trying to do here is change the number of times I compound and see what happens when I compound continuously, an infinite number of times. So if you look at the equation we got, can't change R, can't change T. All I got is this part, and I can't change P either. Can't change the amount of money the loan is for. So I've got this, 1 plus 1 over U to the U power. And I'm going to graph that because I want to know what happens when that number, because that's just a number, right? If I know what U is, I can calculate what that number is, and it's going to be a number. So what's the biggest that number can be? You'd think it could be infinite, but that's actually not the case. If you draw that on your calculator, it ends up looking like this. Okay, it says y equals 1 plus 1 over x. Instead of U, I used x. But you see when you see that graph, that there's a number right there, that yellow line. That's an asymptote to this graph. there's no way that that blue line is going to go over that yellow line. And it's certainly not going to get all the way to 3. So that has a limit. It will not go higher than that number. That number where that yellow line is E, lowercase e. It's for Euler's number, named after the man who discovered it. So what is E? Well, the value for E is actually this number, and I'm just going to talk through it as it goes around, because it's just like pi. You know how pi has no end and never repeats, and you can't write it as a fraction? Well, E is the same way. Just like you write pi is about 3.14, E is about 2.72. It's one of the 5 most important numbers in mathematics, and we're learning about it now. And so, fortunately for you, there's an E button on your calculator, just like there's a pi button on your calculator, and you can use that when we have to do this in the math. So if you look at what we had, right, we had that formula on that green box. Well, we already decided when we graphed that green box that the biggest that green box can possibly be, which would be the biggest that my amount for my loan could possibly be, is going to be E. Okay? So if n goes to infinity, if U goes to infinity, n goes to infinity. So everything is going toward the value of that green box moves toward E and cannot be bigger than E. So if I assume n is infinite, then E is the biggest I'm going to get. So the amount that I have is amount equals P times E to the RT, so PERT. So now I put in my numbers for that, 200,000 E to the, and then 0.4 times 30, and I get $664,023.38. Okay, that's clearly the most money I've had so far, so continuous compounding for the win. All right, so we're going to have a couple of continuously compound problems, as well as a few graphing problems. Really all you have to know from that whole last thing that I did with interest, you have to know how to use the PERT formula. That's what the homework's going to be about, and that's what we'll do, that's what we'll discuss in class next time for the next lesson. Okay, good luck, and see you next class.